Welcome back to another Calculus 2 video. Today, strangely enough, is going to be nearly all about differentiation, differentiating some really weird stuff. Let's start off with a familiar friend, a continuous function lowercase f. Let's let him be continuous on an open interval containing a, and let x be any number in that open interval. What is the value of this derivative, the derivative of that area function? Well, we proved in the FTC proof video that area function, which we more tersely labeled g, was in fact an antiderivative of lowercase f. So in fact, we've done the groundwork to answering this question, i.e. G prime is f, i.e. the derivative of g with respect to x is f, and most complexly notation-wise, but exactly the same thing conceptually, the derivative of the area function with respect to x is f of x. Well, that's exactly what we're trying to find here, so the question mark is just an f of x. But this result is often called the second fundamental theorem of calculus, but once again, strangely enough, we proved the second fundamental theorem of calculus as the first step in proving the first part of the fundamental theorem of calculus. So there was some really good method to the madness. We did the groundwork already. And the payoff is this. If our lower bound is a constant and the upper bound is an x, the value of this derivative of this integral is just the inside function with t's replaced with x's, as you can see underlined in yellow. And moreover, now that we know the FTC from that proof, we have another way of tackling stuff like this. If you're not convinced, for whatever reason, that this derivative of this area function is not f of x, or you're not convinced that is f of x, just apply the FTC. Lowercase f, capital F, a value from a to x, stick that x on in, distribute the derivative, take those two derivatives. First one is f, the second one is 0 because it's a constant, and we have ourselves a lowercase f of x. Who would have thought? Who would have thought we could take the derivative of things that look so nasty but are so easy? But what if we had some funny business? What if that lower bound is a variable? What if we have a variable on the bottom? What are we to do? Well, we apply some even weirder integration properties, the flippity-flip one. We flip that integration symbol, and we can do that as long as we stick a negative sign. And if we do that, well, look, the flippity-flipped integral matches the derivative with respect to x of the area function whose lower upper bound is x, and we get a negative x squared. It's just a plug and chug. Or just a replacement of t's with x's. Alternatively, let's let lowercase f be t squared, capital F is ... We actually don't care what it is, even though in this case we can easily solve for it. Take the derivative, distribute the derivative operator, and proceed exactly the same as the last one, except we are going to stick a negative sign, or we have a negative sign in front of the x squared. That's the only difference. How about we up the difficulty level of life? What if the variable in my upper bound does not match the variable of differentiation? They don't match. What are we ever to do? Well, when in doubt with derivatives, it's always a sure bet to chain rule it out. So we're going to chain rule this guy. We're going to match the variable of integration, the upper bound anyway, is an x cubed. So here I have set up a chain rule expression. Those two terms that I've underlined in yellow, they cancel each other out, they offset each other, so to speak. And now that first term of the product, the x cubed and the x cubed match, I'm allowed to use my second fundamental theorem for my first part. My second part, of course, is 3x squared, and I get 3x to the 8th. Now downstairs here, you can see I'm doing the exact same problem, just an alternative way. Using the FTC, applying the FTC, get your capital F, you stick your upper and lower bounds in, then you take the derivative, you distribute that derivative operator, that last term becomes a 0. That first term, you're going to have to chain rule it out. But we're not dealing with as many integration symbols, it's more familiar territory. Second piece is 3x squared. That first piece is, just the derivative of the antiderivative. So x cubed, the whole thing squared. All in all, gives us a 3x to the 8th. That's all there is to it. Now, I think it's high time for us to live life on the maximum difficulty setting here. What if we don't have any constant bounds of integration? What if both our bounds of integration are variable? Well, never fear. Let's just stick some constants in there. Let's just pick some number a that's in between sine and x squared, and that's our constant. We like that second integral because our constant's on the bottom, but not so much that first one because we don't want the upper bound to be a constant, because then we can't apply the second fundamental theorem of calculus. But easily with integration properties we can make him fit that second fundamental theorem form. We flip him and stick a negative sign. And now here we have two very nice integrals. But again, the upper bound are variables that don't match the x, so we're gonna have to fall back on the chain rule. We will have to fall back on the chain rule. But that's no biggie. Those are my two chain ruled amendments underlined in yellow. And I'm left with this guy in a nice happy cloud. Nice happy cloud. There is my second fundamental theorem of calculus at work in the most complex of scenarios. Or not the most complex, that's just a personal judgment. I'm sure you can think of other ones. But there you have it, that's the way the cookie crumbles. In a sense, this video is really nothing more than an extension of the FTC proof. Just teasing out its implications.